Just a brief presentation, although most of you probably know us since we've been working in several projects that have been presented here, both Floyd, Insect, and in this case, Steroid. We are a research-driven entity, whose goal is to do an interface between academia and industry to bring the great ideas that exist in our academia and push them a bit over and increase the TRL so that it becomes closer to production in industry. And our main goals are to work on the safety and security technological bricks and tools for cyber physical systems, which should be mostly based around safety and security. So some numbers not very relevant. We have been growing and participating in several projects, which some of them are here present. But let's talk about Steroid in particular. So what is Steroid? What we wanted to have with the Steroid? A platform for verification and validation of autonomous driving and ADAS components. So nowadays, we have been talking a lot about autonomous driving and how the cars are connected and the software on wheels and all those terms and definitions. The truth is, our cars have been having increasing complexity in the software in everything that they do. And the software for these cars needs to be tested and validated. And so besides all the existing verification and validation methodologies that exist during software development, there is a lot of extra systems that we would like to understand how they are working and in an integrated way. And when we are talking about autonomous driving, well, it's dangerous to go on the road. It's a lot of logistics to get everything up and running, to get the correct scenarios and edge cases that we want to test is also quite difficult to have. Not to say the danger of producing those edge cases. So what we wanted was to create, to give the tools to create a platform that allows to test and validate what is the end result of this autonomous driving software. For that, we go with a simulation. Let's build a simulation environment where we can simulate everything that is involved in autonomous driving, in autonomous connected mobility in general. And we focused particularly in a T-junction use case where we can have a lot of complexity and different scenarios. In this case, we may have an ego vehicle. Let's consider the vehicle that is under test. So basically all of this, I think we can summarize it to let's test and validate a software that is driving the car, a third-party software. So whoever produces a software, they want to test how they behave. Let's create a platform that is completely unrelated to do those tests, a sandbox, if you like, to just throw this autonomous driver, and see how it behaves. A driving exam in some way. So in this case, we had to provide the whole world for this driver to drive in, which is comprised of connected vehicles, of pedestrians, even legacy vehicles, who knows. And the car exists there. In this case, one small visualization of this intersection running. We have several vehicles. So the vehicle that is coming on top is the ego vehicle. That one is being controlled by a third-party software. The other two vehicles and the pedestrian are being controlled by our platform. So it's the world, the NPCs, if you like to make the parallel with the games, are the NPCs that are populating the world, behaving as it was defined by the user. And well, let's see how our driving software behaves, and let's evaluate how it behaves. So to achieve this, we wanted to have, so besides the driving simulator, obviously we need a driving simulator. For that, we are using Carla, and I think we all agree that autonomous driving will not exist without communications. So we also needed some network simulator to close all this loop, so that our vehicle will surely, the software that we have no idea what is there, but surely we'll be expecting to have other vehicles communicating with him and sending cams and DEMs and CPMs and whatever V2X messages. So we also wanted to get this, for simplification, let's call R3 an R3 simulator, although it's a framework, but let's call it that way. We also wanted the user to be able to define the scenarios in an easy way. So let's stick to the existing standards also, open scenario for defining dynamic driving scenarios. Our simulator, our driving simulator is compatible with the open scenario, so let's go with it. And on top of all of this, we put everything working together. On top of this, let's build our monitors to actually evaluate and validate what is happening. So runtime monitoring with form methods approach. These monitors are also self-generated by a DSL that has been developed by us at Vortex. So since we have multiple situations, multiple entities here involved, we needed to come up with a way to connect everything to create a standard way for them to communicate. So we will end up, so why not use ROS, Robot Operating System, which is a great communication framework, inter-process communication framework. And also we need several pieces here. We need to have the Carla simulator, which works as a server. We have the scenario runner, which interprets the open scenario and executes, spawns everything and executes it in the Carla simulator. We have the R3 itself with all the adaptations needed to have this communication with the Carla. Then we have a set of monitors that need to be launched to do the evaluation of all the scenario. So for that, we also need our manager that deals with all of this. The idea is to do automatic deployment and to facilitate the continuous integration and continuous development. Hence, we prepared everything to run in batches. So you can imagine we have a directory with a set of open scenario files described. Our manager just gets in there, sees for the scenarios of this directory what we need. I need the simulator, the broker, the R3, and the monitors. These two monitors, okay. Then it deploys everything, runs everything overnight. We can think of it running overnight. In the end, we have the results of the monitors. Let's go for the next directory, next batch of tests. So the idea is to have or to use this kind of platform within the development cycle. So not necessarily only in the end, but to make it agile to do smaller increments in the development of an autonomous driving software, which is complex by definition. So another thing or other scenarios that we have for running all of this live with the Carl and so on, it needs a powerful computer for simulation. We also wanted to integrate it with existing situations that there are several, and for that, even here in Aveiro, we have one of the partners of the project is IT, which has already an infrastructure in place. They have logs of V2X messages. So why not also replicate situations that existed in reality? Let's just recreate them in the simulator, and again throw our ego vehicle and let's see how it behaves. Let's see if it can deal with whatever situation has happened before. So all of these different pieces, we have it configurable in the batches. So I'm really just finishing time. So in a very quick way, this is one of the tools that we also have, where we have the ability to create even more chaos in all of this. So let's just spawn a vehicle in the middle of that intersection at any time. The user can just open interface. Let's create a vehicle there, which is a crashed vehicle at some point. All our world, or all of the NPCs that are being controlled by our platform at this point, if they are within field of view, they should be sending the DEN messages, so that again the ego vehicle software should be expecting them. So let's provide them all of this. Next steps, CPMs, CPM messages for the sharing of the cooperative awareness, and later on, hopefully also the maneuver messages, the MCMs, MGMs. Um, so that's basically it in a very fast way. I'm already over time. Platform for allowing us to do scenario-based testing with runtime monitoring, live monitoring for accelerating the development of AD systems.